Welcome back, students, for another one of my videos for the New South Wales Higher School Certificate Physics syllabus. This video is for the Year 12 syllabus for Module 6, Electromagnetism. And one of the topics we are required to investigate there is that students shall investigate or analyse the principles of operation of DC motors and generators and AC induction motors. Now I'm going to talk about AC induction today, and in particular we're going to do a demo of something called Arago's disc. Now a little bit of historical background. Dominique Arago was a French physicist, and he wasn't the first person to discover this strange phenomenon of electromagnetism, but he was certainly the first person to write it up properly and to present it to a scientific audience. Now what was discovered was originally that if you had a magnetized needle, such as the needle of a magnetic compass, okay, and you suspended that magnetized needle from a string, and then you had a spinning disc of a conducting metal like copper, and you spun the disc underneath the magnetized pointer, then what would happen, even though the copper disc is not itself magnetic, that the spinning copper disc would induce a spin in the compass needle. Now this was very strange, and a number of scientists repeated the demonstration and discovered that it was quite easily reproducible, and then they discovered that it worked the other way as well, which was that if you had a stationary conducting disc and you spun the magnet underneath it, then the disc would also start to spin. Anyway, Arago managed to get his name forever associated with this, and so it became known as Arago's rotations. And the particular demonstration we're going to do today is Arago's disc. So this is what's required. We have here a disc made of annealed aluminium, so it's a very good conductor, and I've painted it with a kind of crosshatch to make its rotation easier for you to follow. And it's suspended from a swivel, so it's free to rotate. Okay, so it's just suspended there. And in order to demonstrate Arago's disc, we have to have a rotating magnetic field. So I'm going to provide that rotating magnetic field with a couple of permanent magnets attached to this rotating axle here, an electric drill. So this is able to spin the magnets clockwise or anti-clockwise as we require. Now the principle of this is that we have to have the rotating magnetic field underneath the disc and sufficiently close so that lines of magnetic flux will cut through the disc. And if these magnets now start to move, then they will induce eddy currents in the disc. And we will analyse those eddy currents in a moment using Lenz's law. So here is what the demonstration involves. We spin the magnets. Straight away, the disc starts to follow the magnets. I'll just let that unwind itself. Okay, so the cotton threads have got a bit of a twist in them, and so now they're going to untwist. And I can reverse the direction of the magnets, make them spin anti-clockwise, put them in position underneath there, get the disc to spin anti-clockwise. Now there is absolutely no mechanical coupling between these spinning magnets and the disc. The cause of the effect is purely electromagnetic through the influence of the field. So let's try that one more time. So we'll spin these magnets slow to begin with, and yep, there we can see the disc is trying to follow the direction of motion of the magnets. And the strength of the effect is proportional to the speed of rotation of the magnets. Remember, this is an electromagnetic induction effect. So the faster the rate of change of magnetic flux as a function of time, that is delta phi, phi is the flux, divided by delta t, the change of time. The faster that rate of change, the greater the induced electromotive force in the disc, and therefore the greater the force applied, or the acceleration applied to the disc. So let's check that. We're going to spin the magnets faster. Yes, and sure enough, we get a greater acceleration the faster the magnets go. Let that unwind. So we'll just reverse that direction. Here we go, fast anti-clockwise. Got a nice spin up there. So what has this got to do with AC induction motors? Well, the beauty of the AC induction motor is that there is no commutator. So the armature of the AC induction motor has no electrical contacts to it. The armature of the AC induction motor is induced to spin by currents that are induced into the armature by a changing magnetic flux around it. And then Lenz's law comes into play, because Lenz's law says that if there is a changing magnetic flux which introduces an electromotive force into this disc, the electromotive force will produce another magnetic field. The induced magnetic field will be such as to oppose the change that caused it. Now, how do we apply that principle to Arago's disc? Well, what it means is that the induced magnetic fields around the disc will be attempting to counteract the relative motion between the disc and the magnets. In other words, the faster the difference in speed between the magnets and the disc, the greater the magnetic induced force in the disc. And Lenz's law says that the motion will be such as to oppose this change. In other words, the disc will attempt to match the speed of the magnets. And by matching the speed of the magnets, it will oppose that change in flux. And when they match their speeds, then obviously they're spinning at the same speed, you have no change in flux. Then delta phi over delta t would be equal to 0. And the disc would cease to accelerate. And at that point, it would be running at a constant speed. Now, this idea that the AC induction motor spins at a constant speed is very important. We say that AC induction motors have a synchronous speed. The armature will spin at some multiple of the rate of change of the magnetic flux in the stator around it. So AC induction motors, unlike DC motors, AC induction motors are designed and operate at a constant rotational speed. That is their synchronous speed. So here is the induced rotation in. So this disc is representing the armature of an AC induction motor, and we are inducing it to spin. We are inducing the motor effect in this disc by having a changing magnetic flux around it. Lovely, there it goes. So I hope you understood that. If you need more reinforcement, go and have a look at your textbook. And of course subscribe to my channel, and I'll see you next time when we do another of our HSC physics videos. Bye for now.